So it's a great pleasure to have someone from Barcelona. Well, this time, let's say, Bashar Saleh is going to talk about rational homotopy theory for the homotopy automorphism of manifolds.
Thank you, and I would like to thank the organizers for inviting me. Yeah, so I will talk about rational homotopy theory of homotopy automorphisms of manifolds, but I will be more general in the beginning. So I will start with an introduction with some notation. So we start with X being a topological space, homotopic to a CW complex. So it's a cofibrant space in the mixed model structure. We say that the homotopy automorphism of X is a continuous endomorphism, which is a homotopy equivalence. And we will denote the monoid of all homotopy automorphisms by H out X. Okay, so why to care about this monoid? Well, the first reason is because its classifying space classifies X fibrations up to equivalence. And this is kind of classical theory. And it has been studied by Stashev, May, Schlesinger, Tanre, and many other. And like it's very classical, but still there are some problems, open problems there, which I will talk about. So this is the first part of my talk. I will be talking quite general. And then I will talk about more recent result by Berlin and Madsen. So they develop new techniques in order to for computing the rational homotopy type of homotopy automorphisms, and they use it in order to prove homological stability for homotopy automorphisms of certain or for iterated connected sums of certain manifolds, and the results are also generalized by Matthias Gray. And in an ongoing project, we use the techniques of Berlin and Madsen in order to look at representation stability of the homotopy groups of the homotopy automorphisms of iterated connected sums of manifolds, and also iterated wedge sums of spaces. So, and this last part, I will just talk about it very shortly. So I will start with the first part, classification of X fibrations. So the classifying space of the homotopy automorphisms of X classifies X fibrations, that is fibrations with fiber equivalent to X, up to equivalence in the following sense. So the set of homotopy classes of maps from B to the classifying space of the homotopy automorphisms of X is in one-to-one correspondence with the set of X fibrations mod out by equivalence. And yeah, I will just mention what an equivalence of X fibration is. So if we have two X fibrations, E to B and E prime to B, we say that a map from E to E prime is a weak equivalence if F is an weak equivalence and makes the following diagram commute. And two X fibration are equivalent if they are connected by a zigzag of such equivalences. And there exists a universal X fibration where the total space is of this form. We take a contractible space on which this monoid acts freely, and then we take the homotopy. We take the product with X, and then we take the homotopy orbit space of this thing, and we map it to the classifying space. And thus every X vibration is given by a pullback of this vibration. So in particular, we have that the cohomology of this classifying space is the ring of characteristic classes of X vibrations. So what I'm trying to talk about in this, what I'm going to explain is how to say anything about the rational cohomology ring. So what can be said about it? So in order to do that, we will review some rational homotopy theory and in particular Quillen's approach to it. So Quillen constructed a functor from the category of one-connected topological spaces to the category of differential graded Lie algebras simply connected, or let's say positively graded. And this functor is kind of it's a complete invariant. So we have that lambda x and lambda y are quasi-isomorphic as DG Lie algebras if and only if x and y are rational equivalent. So yeah, it's a complete invariant. But more than that, it induces an equivalence of categories. So when we take the category of topological, one-connected topological spaces and localize it with respect to rational equivalences, then this becomes isomorphic to the category of positively graded DG Lie algebras localized at quasi-isomorphisms.
We can't see very well. Can you scroll down maybe a bit?
Oh, really? Okay.
Or maybe I'm the only one, but I can.
So what about everyone else?
No, okay. The last sign I see is this equivalent sign. So is there something below top or below DGL? Is there something below? No?
I don't know. Maybe I should try.
Yeah, Najib is also saying that part of the slide is missing. Voilà, wait, exactly. I couldn't see, you see the horizontal bar with rational equivalence and quasi-iso.
Okay, let me try with.
Maybe you put it in full screen or something like that.
I did on full presentation, full screen. Let's. Is this better? Let's see.
Okay,
let's try this.
Can you come back to see, to check?
Wait. Let me.
Sure.
Let me try something else.
So everybody says you should remove the thumbnails option. But we tried before, but we were not successful doing it.
What about this? Do you see this Foxit reader thing instead?
Right now it seems okay, but hold on, contains thumbnails. Anyway, fit with, well, anyway, right now it seems to be okay, but we will ask you.
Do you see when I shift to the other presentation, or do you not see that?
No. So far we see only. You see.
Let me stop sharing and then share again. So sorry.
Okay, good.
I'm sorry for this.
No problem. We have time.
So let's try with another view.
Yeah.
And then
fit visible maybe, or yeah. This is okay. I mean, I think we see everything. It's a bit smaller, but we see everything on the screen right now.
Okay, let's stick to this. I'm sorry.
No problem. Yes, we see Bashar Saleh in Universidad de Barcelona.
Okay,
so we have everything right now. Thank you.
Okay, so yeah, so we have an equivalence of categories when we localize the category of topological one-connected topological spaces, and when we localize the category of positively graded DG Lie algebras with respect to quasi-isomorphisms. Okay, so from now on, we will just assume that X is simply connected. And we say that Dirichlet algebra, Lx is a model for X if Lx is quasi-isomorphic to lambda X. So now, okay, if we want to study this space from a rational homotopy point of view, I mean, this is not really possible in the classical sense, because in general, it's not simply connected. It's not even nilpotent. So we cannot model it by Dirichlet algebras in the classical sense. So how to solve this problem? Well, let us, instead of considering all fibrations, let us restrict ourselves to fibrations in the category of simply connected spaces. That is, fibrations where the base space is simply connected. And since we're assuming X is simply connected, I guess then it will be automatically that the total space is simply connected. So let us just consider those fibrations. Okay, so fixing such a X fibration, this determines an equivalence class of X fibrations, I mean, which is determined by some map from B to the classifying space of the homotopy automorphisms of X. So let's take a closer look at this map. So we have such a map. Okay, let's take the loops on it. B was simply connected, so the loop space is connected. Okay, so we have a connected space going to something that is weakly equivalent to the monoid of homotopy automorphisms of X. And this is in general disconnected, but this is connected, so it will land in the connected component of the connected component of the identity, since the identity is sent to the identity. So we have a factorization like this. And now let's take the classifying space again. And then we get back our space B up to homotopy. And we get the classifying space of the homotopy automorphisms of X. But it factors through the classifying space of the identity component of the homotopy automorphisms of X. So we conclude that F factors through this, and whenever B is simply connected. So this is not true if B is not simply connected. And in particular, we can say that the classifying space of the identity component of the homotopy automorphisms of X classifies X fibrations up to equivalence whenever the base space is simply connected. Okay, so it's kind of a classifying space in the category of simply connected spaces. But now note that the classifying space of this monoid is simply connected because this group or group-like monoid is connected. So its D-looping will be simply connected. Moreover, we have that, I mean, the inclusion of this identity component into the whole monoid of homotopy automorphisms induces a map on the homotopy groups of the classifying spaces, which will be an isomorphism for m greater than 2, the higher homotopy groups. So this is a simply connected space, and it has the same m homotopy groups when m is greater or equal to 2. So we conclude from this that the classifying space of the identity component of the homotopy automorphisms of X is weakly equivalent to the universal cover of the classifying space of homotopy automorphisms of X. And there's a theorem saying that the classifying space of the homotopy automorphisms of X, or taking the identity component, is the rationalization of this unrationalized version. So in particular, the rational homotopy type of this space is determined by this space, and this space classifies all XQ fibrations in the category of simply connected rational spaces. Because I mean, if the codomain is rational, then you can just replace the domain by its rationalization. So this is really what we have. So we should look for in order to determine this, we should look for the space that classifies all XQ fibration in the category of simply connected rational spaces. Okay, so let's LX be a cofibrant DGL model for X. And an X fibration in the category of simply connected spaces is modeled in the category of differential graded Lie algebra by an LX fibration there. And what is an LX fibration? Well, it's just a short exact sequence like this, where GE is a model for the total space, and GB is a model for the base space. So a differential graded Lie algebra that classifies all short exact sequences of differential graded Lie algebras with fiber LX should in some sense be a model for this thing, because there is one-to-one correspondence between homotopy types of short exact sequences of this type and of this form and X fibrations. Okay, but to classify all short exact sequences of DGLs with fiber LX, this is a completely algebraic problem. So it's probably an easier problem. And yes, since it's probably an easier problem, it's solved. So by theorem by Schlesinger, Stashev, and Tanre, there exists a universal LX fibration. So you have fiber LX, and then you have a total DG Lie algebra. I will not go into details. And then we have a classifying Lie algebra. And it's universal in the following sense, that any differential graded Lie algebra H, there is a bijective correspondence between DGL maps from H to this classifying Lie algebra and LX fibrations.
Even if you don't want to make any details, but there are derivations, but S of LX is just the degree shift?
This is just the shift, yeah.
Yes,
this is
okay,
just
okay, thank you very much.
With the abelian.
Oui.
So yeah, and two LX fibrations are equivalent if and only if their corresponding maps H to CLX. So they are LX fibration with base H. They are equivalent if and only if their corresponding maps from H to the classifying Lie algebra are homotopic. So a map from H to the classifying Lie algebra correspond to the LX fibration that is given by the pullback. So as a corollary, I mean, this is just we have a universal LX fibration in DGL that should be a model for the universal X fibration in the category of simply connected spaces. So this is a model for the universal cover here. for the universal X vibration in the category of simply connected spaces. So this is not the universal X vibration. I should write the universal X vibration in the category of simply connected spaces, because we have taken the identity component. So let's analyze this total Lie algebra. As Bruno said, we have this is the shift. So this is contractible. So at the end, we get something that is equivalent to the derivations. And we have that this total Lie algebra is a model for this total space, to this space. And let's analyze this space as well. So X can be seen as the homotopy orbits of the homotopy automorphisms, the pointed homotopy automorphisms of X in this. So it's given by this homotopy quotient. And now we can move this thing to the other side. So this is weakly equivalent to this homotopy quotient. And I mean, here we have a contractible space on which the identity component of the homotopy automorphisms of X acts freely. This is a submonoid, so it acts freely also on this. So we could just view this as this thing, E of the pointed version of this thing. And now we take the quotient and we get the classifying space. So as a corollary, we have that the derivation Lie algebra is a model for the pointed homotopy automorphisms of X. Yeah, that are homotopic to the identity. Well, so now we have like models we have models for these things and for the classifying space of the homotopy automorphisms of X, the identity component. But we would extend it. We would like to compute the cohomology of the classifying space of all homotopy automorphisms, not only those homotopic to the identity. So we have a model for the universal cover. So given a universal cover, we have that it is a pi1y bundle. So it's therefore encoded by a map from Y to the classifying space of the fundamental group of Y. And the homotopy fiber will be the universal cover. And now applying Serre's spectral sequence to this homotopy fibration, we get the following. So we take the cohomology of the classifying space of the fundamental group of Y with coefficients in the cohomology of the universal cover converges to the cohomology of Y. And we have that this group acts on this cohomology group by deck transformations. And yeah, this spectral sequence is called the universal cover spectral sequence. So now let us apply this to our case. So if Lx is a Lie algebra model for X, then the Chevalier-Eilenberg cohomology of Lx is isomorphic to the cohomology of X with rational coefficients. In particular, we have that the cohomology of the classifying space the classifying Lie algebra of Lx is equal to the cohomology of the universal cover of the classifying space of the homotopy automorphisms of X. So applying the universal cover spectral sequence to homotopy automorphisms, we get first the fundamental group of the classifying space of the homotopy automorphism, and this is isomorphic to the group of components of the homotopy automorphisms of X, and with coefficients in the Chevalier-Eilenberg cohomology of the classifying Lie algebra of Lx, and this converges to the cohomology of the classifying space, to the ring of the ring of rational characteristic classes. And then, I mean, here we have rational models. This sometimes we understand it, sometimes not. But what we need to understand is the action of this group on the cohomology, right? Otherwise, we will not be able to compute this spectral sequence. And sometimes this action is well understood, sometimes not. So an explicit action of this group on a Lie model for the universal cover would make us understand this spectral sequence much better. But as far as I know, there is no such model equipped with such a group action. Sometimes you can find it with this ordinary DJ Lie algebra, but there is no universal way of doing it, as far as I know. So a problem, an open problem is find a DJ Lie model for the universal cover of the classifying space of the homotopy automorphisms of X, equipped with an action of the group of component of the homotopy automorphisms of X, which model the ordinary action of this group on this space. So can we find such a Lie algebra? Then this action would be known in general. Yeah, and I guess with this problem, I would like to end part 1 of my talk. So now I will talk about more recent results, mostly due to Alexander Berlund and Ib Madsen. So we start with a closed d-dimensional manifold. And let Xn be the n-fold connected sum of M minus a disk. So the picture you should have is something looking like this. Okay, so we observe that Xn plus 1 may be obtained from Xn by attaching a copy of M minus 2 disk along the boundary of Xn and a boundary component of K. So we start with X1, say, and then we take M minus 2 disks, so this one, and then we attach it along one boundary component of K, and we continue like this. So a homotopy automorphism of Xn does not in general extend to homotopy automorphism of Xn plus 1 in any canonical way. However, any homotopy automorphism that restricts to the identity on the boundary extends to a homotopy automorphism of Xn plus 1 that fixes K pointwise. So if we go back to the picture, if we have a homotopy automorphism that fixes this boundary, then we can just extend it to a homotopy automorphism of this, which is the same on this part and then identity on this part. So we get stabilization maps. And we will denote the monoid of homotopy automorphisms of a manifold that fix the boundary pointwise by the following. So we have a curly D as an upper index. so by above, we get a sequence of, I don't know, here I wrote inclusions, but we get a sequence of stabilization maps. So a map here extends to a map here, and so on. And then the question is, can we use the rational models for the homotopy automorphisms in order to prove rational homological stability for this family of monoids? Actually, they are group-like, so we could just view them as groups and like thinking about it as rational group homology. So Berlin and Madsen prove homological stability for iterated connected sums of products of spheres of the same dimension, and describes this stable homology in terms of graph homology in the conservative sense. And then Gray used their techniques in order to prove homological stability for iterated connected sums of products of spheres of possibly different dimensions with some restrictions on n and m, but he didn't compute the stable homology. And I will now describe the techniques by Berlin and Madsen. So the idea was to push this problem to become as algebraic as possible. So by Poincaré duality, we can give the rational homology of the n-fold connected sum of M, a graded symmetric inner product space structure. The inner product is given by intersection form. And yeah, I should maybe say that M should be simply connected. And now, removing the top cell of this thing, well, and taking the d-suspension of the reduced homology of xn, meaning the n-fold connected sum of M minus a disk, this gives us a graded antisymmetric inner product on it, and it's non-degenerate. So for any basis for this space, there exists a dual basis given by the following property. So this is the Kronecker delta. So if I equals j, then we get 1, otherwise we get 0. And now let omega n be just the following sum. You take the free Lie algebra on this homology, on the d-suspension of this homology, and then you take omega n to be this sum. So you take the Lie bracket of alpha e with its dual basis vector, and then the map given by the DJ Lie algebra map, which sends so we take this is a model for the sphere, and letting x go to omega n is a model for the inclusion of the boundary of xn to xn. What's interesting here is that omega n and this map is completely described in terms of the inner product. So there is actually no geometry here. It's just like, okay, you have an inner product on this inner product space, then you can get some omega n. And yeah, for any inner product space V, we may form a canonical element omega V in LV. And this is also independent of the chosen basis. So this thing is independent of how we choose alpha I. Okay, so now the theorem by Berlin and Madsen says that the positive truncation of the derivations on this Lie algebra that vanish on omega n is a Lie model. Is a Lie model for the classifying space of the identity component of boundary relative homotopy automorphisms of Xn. So now we have Lie models for those. Okay. In general, the association V goes to derivations on LV that vanish on omega V is not a functor. I mean, derivations has it has both the domain and codomain being LV. So this is not functorial. However, restriction this association to the category of graded inner product spaces, we get that this association becomes functorial with respect to maps that preserve the inner product. So if we have a morphism of inner product spaces, meaning that it preserves the inner product, we get a graded Lie algebra map, F star from the derivations on LV that vanish on omega V to the corresponding one for when V is replaced by W. And yeah, so we have a map in the reverse direction, W to V, that is the adjoint map to F that satisfies the following equality. So we have a map that goes in the reverse directions, that goes from W to V. So we apply it first, then we apply our derivation, and then we go back by this. So this is really having a derivation here, we get the derivation here. So in this way, it becomes functorial. And Bellon and Madsen proves that the functor from the category of graded antisymmetric inner product spaces of degree k to the category of graded vector spaces that takes an inner product space V to the derivations on LV that vanish on omega V is equivalent to a polynomial functor. So I will give an idea of the proof. So given a sigma module, which is a collection of sigma I representations, I should have an I here, not an M. To every such module, there is an associated Shor functor. So we map V to the following direct sum. And Shor functor is a special case of a polynomial functor. So actually, we will show that V maps to this is a Shor functor. So we start by considering the following short exact sequence. We have the derivations on LV. We compute it on omega V. We have the evaluation map here. And then the kernel will be the following Lie algebra. And we need the surjectivity of this evaluation map follows from the construction of omega V. So I will not go into details, but it's surjective. So this is really a short exact sequence. And let's analyze this. What is this? Well, this is just the following Shor functor. I mean, V goes to this is a Shor functor. You just take the Lie operad and you take the array to M and tensor it with V tensor, the n-fold tensor product of M of V with itself M times, and we let M vary from 2 and upwards. So this is a Shor functor. So V goes to this is a Shor functor. We have also that the derivations on LV is a Shor functor. So I mean, a derivation on a free Lie algebra is determined by its restriction to the generating vector space. So we have an isomorphism like this, and we have an isomorphism now like this. And now, since we have that V is an inner product space, then we have an isomorphism like this, which is canonical, given by the inner product. And I mean, this is something of this form. So we take Lie K tensor with the K plus one n-fold tensor product of V, and we just rewrite it this way again, and we see that it's a Shor functor again. So we have V goes to this, it's also a Shor functor when we have a canonical isomorphism from V star to V. This is the dual of V. So we have a Shor functor here, we have a Shor functor here, and one can show that this map is coming from a map of Shor functors. So we can show that this evaluation map corresponds to a map of Shor functors. So the conclusion is that the map going from V to the derivations on LV that vanish on omega V, the kernel of this Shor functor map evaluation of omega V on omega V is also a Shor functor. So this is also a Shor functor. But more than that, Berlund and Madsen shows that it's given by the following Shor functors. So Lie double bracket M is the Lie operad at arity m-1 seen as a sigma m module, and this is possible. So this is because Lie is a cyclic operad, and the sigma m-1 action extend to a sigma m action on this sigma m-1 module. And I mean, I guess I don't know much about this graph homology thing, but I guess it's because of this. I mean, Kontsevich associated to cyclic operads graph complexes, and from this they could also do this association with the stable homology with the graph complexes. So if Lx is a DG Lie algebra model for X, then the Chevalier-Eilenberg complex has the following two properties. So the Chevalier-Eilenberg homology is isomorphic to the homology of the space with coefficient in X. I said it in the previous part, but also the following functor taking a DG Lie algebra to the Chevalier-Eilenberg chain complex of Lx. When we view this as an endomorphism on graded vector space, this is also a polynomial functor. So thus, if we take the composition, so this thing was a polynomial functor, V to this is a polynomial functor, and then we apply this again. This is again a polynomial functor, and the composition of polynomial functors is again a polynomial functor. So we can just view this thing as a polynomial functor applied to V, to an inner product space V. So now let's look at this. So if we have Xn, which is like, okay, you take the n-fold connected sum of a manifold with itself, and then you remove a disk from it. Well, this is equivalent to the wedge sum of these spaces, of these manifolds with a disk removed. So we have a weak equivalence like this. So let H be the desuspension of the reduced homology of X1. So in particular, we have that the reduced homology of Xn, which is equivalent to a wedge sum, is just the direct sum of the reduced homologies. So in particular, now we could model the stabilization map here by by maps of derivations. So a model for this thing is given by a map from the derivations on LHN vanishing on omega n to the derivations on LHN plus 1 vanishing on omega n plus 1, where a derivation on this Lie algebra is sent to the extension on this Lie algebra that vanishes on the lost summand of this. So you take a derivation, you just let it vanish on the first lost summand, and it acts as before on the first n summands. So again, we use the universal cover spectral sequence. So we have something like this. And now let us analyze, and we want to prove twisted homological. So yeah, proving twisted homological stability for this spectral sequence will give us homological stability for this thing. And here we have Lie models and stuff. Here we don't. So it's better to prove homological stability on this side, or it's easier probably to prove homological stability here than here. And the twisted homological stability here implies homological stability here. So it's it's enough to prove twisted homological stability for this sequence as n gets larger. And now let's just do some simplifications. So here we have pi1 of the classifying space. This is the same thing as the zeroth, the group of components of homotopy automorphisms of Xn that preserve the boundary. And here we take the Chevalier-Eilenberg homology of the derivations. And this we can simplify like this. And I mean, the thing is, okay, so here we have the cohomology, the Chevalier-Eilenberg cohomology of this thing. I mean, this is the Chevalier-Eilenberg complex is a polynomial functor, and we would like to use that property. So there is a theorem saying that by Berlin and Madsen that says that if this group, I mean, the group that acts on the homology groups is commensurable with an arithmetic subgroup of a simple algebraic group of rank at least 2, then the twisted homological stability for this sequence, and with the homology replaced by the Chevalier-Eilenberg chains. So this is much bigger than this, but on the other hand, it's given by a polynomial functor. If we can prove twisted homological stability for this, then it will imply homological stability for this. And this happens sometimes. And the main observation is that this thing is a polynomial functor applied to H tensor, the direct sum of H with itself n times. And there is such polynomial functor P. And for certain xn, for instance, iterated connected sums of certain products of sphere, Berlin, Madsen, and Gray shows homological stability by making use of already existing stability results that may apply for certain arithmetic groups and for polynomial functors. So they really use this property of this being a polynomial functor in order to prove their stability results. Okay, so here's the theorem by Berlin and Madsen. So if M is the product of SD with itself, and Xn is given by this, then the stabilization maps induces isomorphism in the following range, and it's a rejection here. And there is an analogous theorem by Gray, but it's more technical, so I will not state it here. But then I thought in my PhD studies, what can be said in general? Like, okay, so we have the universal spectral sequence here. And then I thought, like, okay, this group is probably easier because here I can use rational models. And then I proved that you can replace this group in this universal spectral sequence by the image of this group in the group of components of the homotopy automorphisms of the rationalization of this space. Okay. But what can be said about the image? I mean, is there anything interesting to be said? I mean, I need more information. And here I will like discuss another open problem. So what can be said here? So in the non-relative case, like if you take just a space and it doesn't need to preserve the boundary or preserving any subspace, possibly a base point, but like not something larger. Then we have by the Sullivan-Wilkerson theorem that the image of the group of components of the homotopy automorphisms of X is an arithmetic subgroup of the algebraic group of the components of the homotopy automorphisms of the rationalization of X cubed. And this happens whenever X is a nilpotent finite CW complex. So we have that this is an algebraic group, and this is the image of it in this group is an arithmetic subgroup. So yeah, this is the statement of the Sullivan-Wilkerson theorem. We have that this is an algebraic group, and this is commensurable with an arithmetic subgroup of it. And consequences of this is that the rationalization, the rationalization induces a map here, which has a finite kernel. And the other thing is that the group, this group is of finite type. So one question that I was thinking about, is it possible to prove a relative version of the Sullivan-Wilkerson theorem motivated by this universal spectral sequence thing? So is it like this, that the following group, when we take the relative version, then this becomes an algebraic group, and this is commensurable with an arithmetic subgroup of this algebraic group? Well, so the way Sullivan proved the classical Sullivan-Wilkerson theorem was by induction on the Postnikov stages of a given space and by using his own models. However, Sullivan models behaves, let's say, badly with respect to cofibrations. So, I mean, here I have a cofibration from A into X. So it's not so nice to use Sullivan models, but in contrast to Quillen models, they are nice. However, Quillen models behaves badly with respect to Postnikov towers. So both models have their strengths and their weaknesses. So at the end, we were not able to prove or disprove a full generalization of the Sullivan-Wilkerson theorem. So it's still an open problem. So by a theorem by Hadrian Espich and myself, so given a cofibration, we were able to prove something weaker. So if A is a cofibration of simply connected spaces of the homotopy type of finite CW complexes, then this group is finitely presented. So this group is an algebraic group, and we have a finite kernel like this. But we don't know if the image lands in an arithmetic subgroup of this algebraic group. So now the last part, which is about FI modules and representation stability, and this is an ongoing project. So I don't have much to say here, but this is another stability results or ways of thinking about stability inspired by the techniques of Berlin and Madsen. So let Fi denote the category of finite sets and injective maps. And the functor from Fi to C is called an Fi object in C. If C is the category of R modules, then we will just call it we just call an Fi object in the category of R modules by an Fi module. And there is a notion of stability for an Fi module V. So let n be the set of n elements. An Fi module V is said to be finitely generated if there exists a finite set of this disjoint union such that there is no proper sub Fi module W of V such that S is also a subset of this submodule. And a key result by Church, Ellenberry, and Farb is that in characteristic 0, being finitely generated is equivalent to have uniform representation stability. So one can just prove that it's finitely generated and you're done. So now let's go back to the homotopy automorphisms. So for a fixed manifold, d-dimensional manifold, and the finite set S, we have that a model for the classifying space of the identity component of the homotopy automorphism, boundary relative homotopy automorphism of the S-fold connected sum of M minus a disk is given by a DJ Lie algebra of this form. And we see that the functor, and then we observe that there is a functor from the category of finite sets and injections to DGL given by the following. So we take a finite set S and send it to this derivation Lie algebra. And then, I mean, this is now an FI-DJ Lie algebra. And then taking the homology, we get a graded Fi module or Fi vector Q vector space. So taking the homology now, it's again a functor, and we get that this thing is an Fi module. And in an ongoing project with Eric Lindell, we are investigating this graded Fi module. We were able to prove that it's finitely generated, so we have uniform representation stability. And we're trying to investigate what does it mean geometrically. So this is what we're working on. Well, I guess that's all I had to say. Thank you for listening.
Thank you very much. It was a very nice talk. Is there any question to Bashar?
I would like to ask one, if possible.
Go.
Do you hear me?
Yeah.
Yeah. So this action that you don't know how to model, I didn't get it very well. But are you trying to compute the deck transformations of B out 1 of X?
So let's go back. Yeah, so right, I have a group action of this on actually on the space here, right? Deck transformations.
Yeah, but I think it was before that. The thing is that you have you have a space X, and then you look at out of X, that's a monoid, and you take the classifying space of the identity components. And that's the universal cover of B out of X.
Yes.
Right, and you want to retain, so if you know then deck transformations of this space,
Yes.
then you know pi 0 of the previous one. So my question is the deck transformation group of B out 1 of X in correspondence with the automorphisms of the derivations of the Lie model of X, maybe of some special form like conjugation?
Well, this is okay. So the thing is, if you take, yeah, it's given by conjugation, but I mean, okay, you have a model for a deck transformation, and then you should have a model for each deck transformation, or for each group element you have a model for this automorphism, and then they together should form a group, right?
Yes. So
I guess it's not so easy to do always.
No, I don't know. I'm asking because that's what one should expect.
So, but you're right. It's given by conjugation, but so if you take a fixed group element or a homotopy class of pi node, then you can model its action, but I don't know if you take all of them, then they will give a group action. I don't know if I'm answering your question.
Oh yeah.
So here it is. So for every element here, I have a map which acts on this, but I should make a choice so that they together, when I take composition and blah blah blah, they land back in those representations. And I don't think this is easy to do, but I don't know.
Okay, thanks.
Is there any other question? Feel free. If not, I have one or two. I didn't quite get your point with the Sullivan model. As far as I remember, when you want to have rational models for mapping spaces X and Y, then you choose a Lie model for one and a Sullivan model for the other. But here X equals to Y. So you chose to use Lie models. How can you choose Sullivan models in this setting?
I don't think you can do that. I mean, even Sullivan himself, he proved the unpointed version. So he has like, so the homotopy automorphisms of a space could also be given by derivations on the Sullivan model, but this doesn't give us a Sullivan model. It gives us a Lie algebra again. Yeah. So it's kind of, I don't know if there is a Sullivan model.
Exactly, derivations are still live in the world of Lie algebras. So,
yes.
Yeah. And well, now speaking of Sullivan model, a Sullivan model is an L-infinity coalgebra, the generators of a Sullivan model. So, and well, L-infinity algebras are simpler than Lie algebras. So I know when I say that, everybody will scream out loud. But the point is that, no offense, huh? But we have no good basis for the free Lie algebra. It's a mess. On the other hand, free L-infinity algebra is very simple, just commutative graphs, commutative trees. So, okay, I'm claiming that L-infinity algebras are simpler than Lie algebras. And it's often easier to get models, I mean, L-infinity models than Lie models. Did you try to play with L-infinity guys instead of Lie guys? No,
no, but it's a nice idea. Maybe that would solve something.
Yeah, so just, I'm saying it again out loud. L-infinity algebras are simpler than Lie algebras. On the opposite to what people might think, because the operand which encodes it is free, and the operand for Lie algebras is a difficult quotient operand. We have no good basis. Well,
that's true, but maybe what is missing is the model of the classifying vibration using L-infinity algebras.
I didn't say we have everything at end right now. You see, the idea is as follows. The idea is to live in the world of L-infinity algebras, where you can get actual formulas. You can get actual formulas, and then you go down by applying the polynomial functor Lie circle on L-infinity. Okay, Lie is an L-infinity module, right module. So you take the free Lie algebra over L-infinity. So working on the level of L-infinity, you can always go down to Lie, not the other way around. Okay, and I'm claiming that on the L-infinity level, you have you have explicit guys, trees, blah 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 blah. You have a basis, you have stuff like this, and in the end, you reduce to Lie and you get your formula. So that was just a comment. Okay, it's just an idea. Okay, is there any other question? Sorry. No? No one? So maybe we can thank Bashar again for this nice talk. Thank you very much.